So, good morning, everybody. It's very nice to have a lot of people here, although I cannot see you. It's a pity we cannot meet everybody in Romania. It was planned, but I hope this will be a nice experience anyhow. So in this session, we have 3 speakers. All of them have 30 minutes to speak, and then we have a questioning period of approximately 5 minutes. And as an audience, you cannot put your questions directly, but you have to write them in the so-called live Q&A section, which is to the right on in your screen. And then I will put them to the speaker. We will just have room for a few questions, unfortunately, but still do put questions there. And after the session, there will be possibility to meet all the speakers in the so-called meet the speakers room, which you will see on in your browser. So you can just join them and then you can speak to them. So it's my pleasure to present the first speaker of this morning, and that is Fernando Martin, and he will talk about imaging electron molecular dynamics towards attosecond chemistry. So welcome, Fernando. You're muted.
Good morning, everybody. I will share my screen. I hope it will work. Okay. Well, it's a great pleasure to be here and to present the work that we have been doing for several years in Madrid. So basically, in this talk, I will briefly outline the key scientific steps that have led to the birth of attochemistry and hence to this attosecond chemistry network, and as well future directions in the field. Of course, my presentation will mainly reflect my personal and partial view of the field, which inevitably has a marked theoretical character because I'm a theoretician. But this view has been developed along the years in collaboration with the main experimental actors in attosecond science. So as most of them participate in this workshop, you will have the opportunity to complement my personal view with theirs. And so for those who are active researchers in the field, most of what I'm going to say is probably well known, so I apologize to them. But I think in view of the marked interdisciplinary character of the workshop participants and the large number of participants that have registered, which is about 300, I think that this kind of presentation may help to bring new ideas to the field and to establish new synergies and promote scientific debate. So I will start by saying what I understand for attochemistry. So attochemistry for me is the visualization of electronic dynamics in real time, that is, in the attosecond time scale, to better understand the chemistry of molecular compounds and eventually to manipulate that motion to induce a different chemical behavior. So it's the application basically of attosecond science to problems of chemical interest, which always involve molecules, simple and complex molecules. So there are 2 ways of doing attochemistry, let's say, so far. One is based on attosecond pan-prof spectroscopies, in which attosecond pulses are explicitly used to ignite and or probe the dynamics that is generated in the molecules. And the other way is to use high harmonic spectroscopies, in which the light emitted through the high harmonic generation process is the observable that contains the information that about the electron dynamics occurring in the molecule. So in my talk, I will only speak about the first one, so attosecond pan-prof spectroscopies, and there are other speakers in the meeting who will address the topic of high harmonic spectroscopy. So it is important to understand that when we use attosecond pulses to induce or visualize dynamics in molecules, one has to take into account that these attosecond pulses are generated in the XUV and X-ray wavelength ranges. That means that absorption of a single photon, as you can see here, leads to ionization. So you will ionize any molecule. And that means you will produce a molecular cation, and this molecular cation can either remain bound or it can lead to dissociation, and so leading to smaller ionic fragments. And the other important thing is that because of the short duration of the pulse, the bandwidth is very large. And here you have a typical bandwidth, superimposed to the potential energy curves of a typical diatomic molecule. And you see that this bandwidth is huge compared to the energy separation of the energy levels in the molecule. So these two facts are crucial to understand the kind of dynamics that one generates by using these attosecond pulses. Here you have a more quantitative comparison between the bandwidth of an attosecond pulse. This is an attosecond pulse of 200 attoseconds, more or less. And you see that the bandwidth, within the bandwidth, you have, many different molecular states. That means that if you shine a molecule with an attosecond pulse like this one, you can ionize the molecule from the HOMO down to the whatever orbital. And the interesting thing is that you have photons of different energies, and that means that you can ionize the molecule from the upper orbitals by using low energy photons. And you can at the same time ionize the inner shells by using photons of higher energy in such a way that the energy that is produced at the end, the energy of the escaping electron, is exactly the same in both cases, which means that you cannot distinguish these two photoionization events. In other words, when you shine a molecule with a broadband attosecond pulse, you generate a coherent superposition of electronic states of the cation, and the coefficients of these superpositions are the ionization amplitudes. So in an experiment, what the goal is to visualize this electronic wave packet, is to see how this electronic wave packet moves in time. And from the theoretical point of view, our role is to provide the ionization amplitudes that allow one to calculate the wave packet. So the dream in attosecond pump probe spectroscopy is to use attosecond pulses for both the pump and the probe steps, so that the pump ionizes and generates some electron dynamics in the molecular cation, and then the attosecond probe pulse comes and takes a picture of the system at a given time. And this time can be controlled by varying the delay between the pump and the probe pulses with attosecond resolution. Unfortunately, this dream is still not accessible due to the rather low intensity of these pulses. So instead, what people have been doing for a number of years is to use a single attosecond pulse to ignite the dynamics. So this step is the same as in the previous case. But for the probe step, they usually use the infrared pulse that has been previously used to generate the attosecond pulse through the high harmonic generation process. So this femtosecond pulse here lies typically in the infrared and is longer than the attosecond pulse. So it typically has a few femtoseconds duration, but the important thing here is that the delay between the pump and the probe pulses can be varied with attosecond resolution. So what is required from theory if you want to investigate these processes? So obviously you have to apply quantum mechanics, because I have been, as I told you, we are talking about electronic wave packets, so we need quantum mechanics. You cannot do this classically. And we also have to describe the correlated motion of unbound electrons in nuclei, because as we have seen, the electrons leave the system, but the remaining cation can break. And so we had to be able to describe electrons and ions that are free, that move almost freely. And we had to do it in the time domain. And the way to do that is obviously to solve the time-dependent Schrödinger equation. And in which you use a Hamiltonian that contains both electronic and nuclear degrees of freedom. And of course, you had to include the potential that describes the interaction between the laser and the molecule. Now, solving this equation numerically is impossible, except for the simplest H2 plus molecular cation. And there are some partial solutions also for the case of the hydrogen molecule. But beyond that, it's nearly impossible to use numerical methods. So you have to use other approximate methods to solve this equation. And a particular method that has been very successful in the past is the spectral method. So in this method, one takes the time-dependent wave function that we want to calculate, the one that is here, and this wave function is expanded in a basis of Bohr-Oppenheimer molecular states. And here you can see three different families of Bohr-Oppenheimer states. So a Bohr-Oppenheimer state is the product of an electronic wave function and a nuclear wave function. And as I said, there are three kinds of products. Those involving bound electronic states that are, for instance, the ground state of the molecule and the excited states of the molecule. There is other group that involves the electronic continuum states of the molecule. So these are the states that are here, that you can see in this shaded area. These are states in which one electron is escaping from the molecule. And there is a third group that contains all the multiply excited states lying in the electronic continuum that are represented here by this blue arrow. And of course, all of them must be multiplied by the corresponding vibrational states and dissociative states. And so when you insert this equation here in this Schrödinger equation here, and you project onto the Bohr-Oppenheimer states, you end up with a system of coupled differential equations in which, of course, here I'm just using a block representation. So every block here corresponds to all matrix elements involving a particular group in this expansion. And as you can see in this system of coupled differential equations, there are different kinds of couplings. There are dipole couplings and non-adiabatic couplings. The dipole couplings are generated by the interaction with the external poles. And there are all other couplings due to the Hamiltonian in case these are not exact eigenfunctions of the system, which is usually the situation. So then what you have to do in order to apply this method is first to calculate the electronic states that appear in this expansion, and then to calculate all the couplings. And then you have to solve this system of coupled differential equations that is usually huge. An interesting point, an important point here is that some of these couplings involve transitions between continuum states. These are, for instance, the transitions induced by the probe pulse when you have an infrared pulse. And these couplings are not easy to obtain. And so this has been a limitation for a number of years of this method, but these problems have been recently solved. And the examples I will show you will give you an idea of the importance of these couplings when you apply this methodology. Now, I don't want to give too many details about how we calculate these things. I will just mention that we have been developed along the years methods that are applicable to molecules of different sizes, for small molecules, for larger molecules, and for very large molecules. And well, you can find the details about these methods in these references. So these methodologies have been extremely important to understand the first attosecond pan-prof experiments performed in molecules. In particular, the first experiment performed on the hydrogen molecule, in which we could show that the observation reflected the jumping of the electron from one nucleus to the other in the H2 plus ion. So showing that for the first time how an electron moves in a covalent bond. More recently, this methodology, but in a more simplified form and without including the effect of nuclear dynamics and without including the effect of the probe pulse, has been used to study the electron dynamics in some amino acids, in the phenylalanine amino acid and the tryptophan amino acid. And what you can see here is the actual electron wave packet that is generated by the attosecond pulse used in the experiment. But of course, this is not what is observed in a real experiment. So in a real experiment, things are much more complicated because this is reality, and reality is always more complicated than our ideal scenarios in theory. So basically, in a real experiment, they shine a molecule with a broadband attosecond pulse, which has a weird spectrum in general. This leads to a molecular cation. Then they come later with an infrared probe pulse that we'll see, and they want to learn by using this probe pulse about this electron wave packet that is generated by this attosecond pulse. So when the infrared pulse comes, this infrared pulse further ionizes the molecular cation, leading to a dication. And this dication will experience some nuclear dynamics that will occur typically in the femtosecond timescale, and later on will break into different fragments. And this will take place in the picosecond timescale. So what they measured in all these experiments I showed you before, what they measured is fragmentation yields. So they look at ions, and they represent these fragmentation yields as a function of the delay between the pump and the probe pulses. And so the main problem of this is that one is expecting to learn from the detected ions what happened here in the pump step. So something that occurred in the attosecond time scale that one hopes survives long enough to be seen in the fragmentation channels. And this is not always the case. This is not easy to do experimentally, but these people succeeded. And but there is a more direct way to investigate these electron dynamics, which is to look directly at the ejected electrons. So in doing so, if you look at the electrons that are ejected at the pump and probe steps, then we don't care anymore about all the nuclear dynamics that comes after the probing step. So the dynamics that will be imprinted in these ejected electrons will be exclusively due to the electron dynamics generated by the pump pulse and eventually by the nuclear dynamics that occurs between the pump and the probe steps, but nothing else. So this will be a much more direct way to look at these problems. So of course, this is easy to say, but experimentally it's very hard to do because, as I said, the attosecond pulses are not very intense, and so this is a very challenging experiment in general. So there is an alternative to this that simplifies the detection of the electrons, which is to use, instead of a single attosecond pulse as a pump, to use a train of attosecond pulses, and to develop a pump probe scheme in which the train of attosecond pulses overlaps in time with the infrared pulse. This is the so-called reconstruction of attosecond beatings by interfaces of two photon transitions, or RABIT. So this technique, in this technique, you detect electrons, and this technique has been used for a while to characterize attosecond pulses. But it has been used recently to learn about the electron dynamics that is generated by this train of attosecond pulses. So basically, when you have a train of attosecond pulses, if you take the Fourier transform of this, you don't get a continuous broadband as in the case of a single attosecond pulse. You get harmonics. You get some peaks here at well-defined energies, and those peaks are separated by 2 times the frequency of the infrared pulse that was used to generate the train of attosecond pulses. As a consequence, when you ionize, for instance, helium, what you will see if you plot the ionization probability as a function of photon energy and as a function of the delay between the train of attosecond pulses and the infrared pulse, what you will see is peaks at around the positions of the harmonics that are resulting from this attosecond pulse train. And you will also see additional structures that result from the interference between 2 processes leading to the same final state. And this is called a sideband. And this sideband appears because you may have absorption of one harmonic photon followed by the absorption of an infrared photon, and this can interfere with another process in which you absorb a photon from the higher harmonic, and then you have a stimulated emission of one infrared photon from that harmonic. These two channels lead to the same final state, then it leads to interferences, and that's why you see oscillations here. And this occurs in between every two harmonics. So what you can do is, it can be shown, although I don't have the time to do it, that if you feed these sidebands to this simple formula over here, then you can extract the phase associated to these oscillations. And this phase is related to the photoionization time. So if you are able to measure these oscillations and get the phases, then you can access the time the electron takes to escape from the molecule. If you have enough energy resolution here, you can also know what is the value of the phases as a function of energy. And of course, you can also get the ionization probabilities. And from that, you can reconstruct the electronic wave packet completely. And this has been done in the case of helium in this paper that you can see here. And what you see here is the reconstruction of the electronic wave packet in helium as a function of time that is obtained directly from the measurement. Of course, in molecules, things are more complicated. And this is illustrated, for instance, by this recent work performed by Laura Cataneo in the group of Ursula Keller, in which the same rabbit technique was used to investigate ionization dynamics in the hydrogen molecule. And the main difference here, although the setup is exactly the same as in the case I showed before, the main difference here is that we have a molecule. And when you have a molecule, the energy that you put in the system is shared between the nuclei and the electrons. This possibility does not exist in an atom because you don't have nuclear degrees of freedom. But here you have nuclear degrees of freedom. So that means that at every time delay between the attosecond pulse train and the infrared pulse, you have a picture that can be as complicated as this one, in which you see that the ionization probability depends on both the kinetic energy of the ionic fragments and the kinetic energy of the emitted electrons. And so you have a picture like this for every delay between the pump and the probe. Now, that means that a full rabbit spectrum in a molecule like this is not a two-dimensional spectrum as the one I showed in the previous slides, but it's a three-dimensional spectrum in which you have a sequence of images like these ones that vary with time. And of course, in order to have access to all this information, you must detect both electrons and ions in your experiment. And this can be done, for instance, by applying multi-coincidence detection methods, as it was the case in this paper that I'm just describing. So if we keep this in mind and we look at the rabbit spectra that you measure, then you will realize, and this is not a big surprise, that the phases that you get from the sidebands, or in other words, the ionization delays that you obtain from the sidebands depend both on the kinetic energy of the nuclei and on the kinetic energy of the electrons. And here you have two examples. One is extracted from a real experiment, and the other one is extracted from our theoretical calculations. So this is something to keep in mind. When you have a molecule, your ionization delays depend on both the nuclear energy and the electron energy, and for the same reason, the wave packet that you generate with the attosecond pulses is both an electronic and nuclear wave packet that cannot be disentangled in general. Now, you don't have a multi-coincidence detection method, which is very difficult to implement in an attosecond setup because of these low intensities of the attosecond pulses. You may also have access to the nuclear dynamics or to the final states of the ion if you have a very high energy resolution in your spectrometer. For instance, this was the case in a recent work performed by the group of Anne Lullier and Mathieu Gisselbrecht in Lund, in which they performed a rabbit experiment in the nitrogen molecule, and they used a train of attosecond pulses with these harmonics, with the idea of ionizing the molecule in a region where there is a shape resonance. This shape resonance is well known from synchrotron radiation measurements. It appears in the lowest ionization channel. So The idea is that when you ionize this molecule or any other molecule, of course, you will be able to leave the N2 plus cation in different ionic states, but you will leave them not only in, you will not only lead to dissociation of the N2 plus, but you can also lead to N2 plus in a bound vibrational state, which are plotted here. So you have resolution to resolve the vibrational structure of the final N2 plus cation. You will know how much energy is left in the ion. And then you can perform plots similar to the ones I showed in my previous slide. So, but this is very complicated in general, because as you have seen in the previous slide, when you ionize N2, you can leave it, you can do it through different ionization channels. And here is what the theory predicts for this molecule when you use an attosecond pulse train as the one used in Lund. And you can see that you have peaks associated to the harmonics for a particular channel, let's say the X channel, but you also have harmonics associated to the other channels that are open. For instance, the A channel plotted here, okay? And in addition, you have the sidebands that appear in between the harmonics, and these sidebands, appear for all open channels. As a consequence of these, sidebands and harmonics overlap most of the time, as you can see here. And it's very difficult to identify, the individual features associated to a particular ionization channel. Experimentally, you do not have access to the individual contributions of the different channels. What you would see is just the spectrum plotted here in black, is the total spectrum. And this reflects, the sum of the different contributions. So what is done usually in order to highlight the sidebands that contain the interesting information about the ionization times is just to compare the rabbit spectrum with the spectrum you obtain by using only the attosecond pulse train that is plotted here in purple, and then you calculate the difference between these two spectra. And the difference will be the effect of the infrared probe pulse. And this will contain information about the sidebands much more clearly. And this is what the actual experiment gives. This is the difference I showed you before as a function of the delay between the pump and the probe. And here you have the result of the theoretical calculation that we performed. And as you can see, they are in very good agreement. But the interesting thing is that you can really see very clearly here, the contributions of the different sidebands, and you can resolve them vibrationally. So then you can fit them and get the phases for every peak you see in this spectrum. And what you obtain by doing so is the following. Here, what is plotted is the time delay difference between the X and the A states when, in both cases, the N2 plus cation is left in the ground vibrational state. And as you can see in the experiment, there is a variation with photon energy that is also reflected by theoretical calculation, although there is a shift in energy here. And this is because, in order to access both electronic and nuclear dynamics in this molecule, we had to lower the quality of the electronic structure calculation. And in doing so, the position of the shape resonance that we obtain is below the actual position that is obtained in synchrotron radiation experiments. So for this reason, we get this result at lower energies. But the important thing is that we see exactly the same variation. And if you look at the highest variation here, which is about 50 attoseconds, this is compatible with the lifetime of the shape resonance I was talking about. So it means that by doing this kind of plot, one has access to the lifetime of the shape resonance. The interesting thing is
Fernando, you have 2 minutes left.
Okay, thank you. I'm finishing. Okay, thank you very much. So, so if you do the same by just choosing only the A state and comparing the time delays for electrons emitted from N2 and leaving the N2 plus molecule in the A state, and you compare only the V equals 0 and V equals 1 levels of this state, well, not surprisingly, you see almost no variation. You see that the delay is almost 0. And this is normal because the energy difference between the electrons associated to these two channels is only 100 milli-electron volts, which is very small. So the variation is very small. But when you do the same in the X state, then you see that this is huge. And again, I'm comparing V equals 0 with V equal 1. And again, the only difference between the two photoelectrons is 100 milli-electron volts. And this is also seen in the calculation. And since I don't have too much time to explain it in detail, I will simply say that this is because when you look at different final vibrational states, you are exploring different regions of internuclear distances. And as a result of that, the potential the electron sees when it escapes through the potential barrier is different, is slightly different. And as a result of that, the lifetime of the shape resonance is different in one case and the other. And this difference is huge because this is tunneling, and just a small difference in the width of the barrier or the height of the barrier has an enormous effect. And this is precisely what is seen in the experiment. So if you calculate the Wigner delays that you calculate theoretically for these two potentials, and you make the difference between them, which is what is plotted in the experiment, you get this curve that compares qualitatively well with the one that is obtained in the experiment, and also explains why below a given energy, this difference becomes negative. So in fact, this experiment, what it's telling us is how the lifetime of the shape resonance varies when we are varying the internuclear distance in the N2 molecule. And with this, I conclude. The conclusions are very general. So I think that the important message from my side is that recent theoretical methods for the electronic continuum are now able to describe realistic attosecond pump-prof experiments in small molecules and have started to do so in large molecules. The other important message is that watching photoelectrons is probably better than watching ions. Ideally, it would be better to look both electrons and ions. And the other message is that so far, you want to reconstruct wave packets, you have to obtain amplitudes and phases as a function of both the kinetic energy of the electron and the energy of the remaining molecular cation. And if you want to know more about that, I recommend you to read this review that we published a few years ago. And of course, I want to acknowledge the work of the people involved in all the results I showed that you can see here. And with this, I thank you very much for your attention.
So thanks a lot, Fernando, for a very interesting and pedagogical talk. I want to remind everybody that if you want to have questions, you need to put them into the Q&A part. So you didn't see me, now you see me, okay. Anyhow, I want to remind everybody that if you want to have questions, you have to put them there to the right. There is this Q&A section where you can write in your questions. But at the moment, there are no questions there, which I can see. So I have a question myself. So in the rabbit experiments, when you do them from atoms, you know that it's very important to account for this continuum transitions. This is what is given by the IR field, and also this gives a large contribution to the delay. So how did you really treat that now for the molecules?
Well, in the molecules, this is precisely a critical aspect of the calculation. So the continuum couplings are included in our simulations. In all the rabbit calculations we perform, these have to be included, otherwise you don't get the rabbit spectrum, okay? And so the way to do this is to work so we enclose the system in a box, and then we get a discrete representation of continuum states. And if you work consistently in a box, then the continuum couplings, are consistent. And you may have heard about problems in calculating continuum couplings when you are dealing with an infinite box, because you have singularities. But when you work in a box, you don't have singularities anymore. and everything is consistent. And so we have been checking this for many years in atoms, in hydrogen atom, and in helium, as you have seen. And we are applying exactly the same methodology for the for molecules. So, and this is the hardest part. And in fact, this is the reason why we had to lower the quality of the electronic structure description of the N2 molecule, because when you had to include a continuum couplings, you have millions of those. And then the size of your problem increases exponentially. And so, but this is very important, because if you include the continuum couplings, you don't have to rely on simplified approaches like this based on this tau CC correction, etc., etc., etc. So what you get from your calculation is directly what is measured, and so you can perform a good comparison.
Thank you very much. I see that now it pops up a lot of questions, so we try some more. Jen Moore asks, how is it possible to achieve such a high resolution in both time and energy, considering the time-energy uncertainty principle?
Well, that's a very good question, but I'm not the one who has invented this concept. In fact, there is a very beautiful paper by the Lund group published in Science, I think a couple of years ago, 3 years ago, where they precisely explain this, that the idea is that you get, very precise energy resolution in your detector, okay? And of course you get a lot of time resolution by varying this. So this is in the detection. Of course, the uncertainty principle is still there, because what you generate is an electronic wave packet. So you are not able to follow the position of the electron, with 100% certainty. So there is no violation of the Heisenberg uncertainty principle, but in your detection, you have a lot of precision. So that's the trick. But I think, since I don't have time to go into the details, I think just check a science paper by Anne Lullier and collaborators published a couple of years ago, I think, and they explained this very well.
2017, I think.
Okay.
Then Anne Hart asks, she says, thanks for a nice talk. On page 25, where does the offset come from, the offset between theory and experiment? Page 25.
Where, sorry?
Page 25 of your talk, I guess.
Slide 35.
Yeah.
Let me see. I should probably share the screen again. I don't know, you can see. No, I didn't share my screen. Okay, it's yes, give me 1 second. Okay, I'm back here. Okay, so 35. No, sorry, I'm not in the.
Yeah, it's not easy. We're so off time.
No, I don't think it's 35, because I didn't have 35.
No. Was it 35? 25.
Ah, sorry, I didn't hear very well. 25. Okay. Okay, here it is. This is the, no. 25 is this one. So I guess the question is about the offset here, this thing here. Well, I tried to explain it. The offset is because the theoretical calculation is not accurate enough, and we know this. So this is the photoionization cross section. This has been measured 30 years ago, okay, in synchrotrons. This is this experimental result. So we can reproduce this shape resonance perfectly with our methods. But then, if you want to do rabbit, you have, as we were discussing previously, you have to describe continuum transitions. And then your problem becomes huge. And it's completely unaffordable from the computational point of view if we keep this level of accuracy. So what we had to do is to lower the quality of our description, so that we are not able to describe the position of the shape resonance accurately, but we still get something reasonable, but shifted in energy. So for this reason, all the results shown here are shifted down in energy. But this is due to the poor quality of our description of the electronic structure of N2 that we had to adopt, because otherwise we would not be able to get rapid spectra.
Okay, I'm sorry, but we don't have time for more questions. You have also a question about the importance of rotational excitations and the advantage of measuring both ions and electrons. But I just repeat this information that I had, that after this session, you can go to the special room and meet Fernando and put your questions to him and chat with him. So that's so this is what you have to do. Because now we have to say thanks a lot to Fernando, and this is with applause, which is not, you cannot hear. And we have to go to the next speaker. And I hope that we have Katarina Vozzi with us. Yeah, here she is. Here she is. So welcome, Katarina.
Hi, thank you.
Katarina has a title, attosecond technologies for the study and control of electron dynamics in molecules. And yeah, welcome and go ahead.
Yeah, here I am. Okay, no, I'm sharing the wrong monitor, sorry. So I should stop it and share it again. So should this one? And we do like that.
No, it's correct, I think.
It's the correct one? Okay, thank you. Just it's not the beginning of the, yeah, okay. Okay, thanks. So thanks, Eva, for the introduction. And this presentation will be about attosecond technology, and particularly basically is the counterpart of what Fernando have shown before, in the sense that I will focus on the experimental techniques. And well, okay, the title is really broad, so I'll tell you now what I'm going to talk about. I will give a brief introduction to attosecond technology, to aims and challenges that we are currently facing, and that are very well within the AutoChem cost action, with also focusing a bit on the high-order harmonic generation, which is the source that we usually use for doing attosecond experiments. And then I will focus on some recent advantage that we obtained in our lab with the new technique for high-order harmonic generation, which seems to be quite promising for, let's say, having a bright source. So, okay, like as Fernando mentioned already, what we want to do is the study and control of ultra-fast electron dynamics in complex system. Here I show a cartoon. I think I can also get, no, do you see my mouse? I guess so. You can see here a solid, but it could be a molecule or any kind of system, like you want to excite it and then follow in time what's happening in the relaxation process. So what happened basically, what is the photo-induced dynamics in the sample? And in particular, we are focusing on the very early dynamics because we are looking at electron dynamics. And so even if we want to study, I don't know, exciton dynamics in a solid, or we want to study, I don't know, the photoprotection mechanism in a biomolecule, we are looking at the very early starting of all of these phenomena. And for doing so, of course, the standard approach is the pump probe experiment. Basically, here we have the actors of this experiment, which is basically the pump and probe source, and then a sample, and then the detection, that the information that we get. Basically, we have a pump pulse that initiates the ultra-fast dynamics in the sample, and then we have a probe pulse that interacts with the excited sample, and at the end we detect something, which could be the pulse itself, the probe pulse, so we look at photons, or it could be if the sample gets ionized, for example, ions or electrons, as also already Fernando showed you as a prototypical in prototypical experiments. And so, like, basically, attosecond technology deals with the development of all those actors, like the development of proper sources for pump and probe experiment. So that should have properly characteristics for being able to perform this experiment with such accuracy and time resolution, but also like the manipulation of sample, which is something that we don't take into account in theory, but then when we are in the lab, we need to put the sample in the vacuum chamber to perform the experiments, and the sample could be of different kind. And it could be quite challenging, this task. And then of course, for the detection, I mean, basically we want to collect some information about the process going on. This could happen detecting different things. And I mean, also the accuracy of this detection and the amount of information that we can collect give us then maybe the temporal resolution and the possibility and the capability to give the right information to theoretician in order to retrieve the information. This is really like very general for pump probe experiments, and in particular for attosecond experiment, like we need very specific sources for instance, for doing that. What are the sources that we usually use for attosecond spectroscopy? Well, mostly it's tabletop sources based on I-order harmonic generation, and I will go into a little bit of detail on this process just in a few slides. But recently we also have, like here you can see a picture of a system in a lab, which is kind of compact. But then like we have free electron lasers that recently achieved attosecond I mean, we have already few femtosecond resolution for pump probe experiments, but I mean, we are able also to generate, collect, and detect attosecond dynamics. And I think we will hear something about that also from Giuseppe Sansone's talks. This is a picture of the undulator, one of the undulator of the PSI free electron laser that I show here. So now in general, which are the challenges that I mentioned before on these experiments that we want to perform? Indeed, we have the development of the laser source. This is also like my main topic, but I mean, it's something which is really, really, it has been the target of a lot of research work in the last, I would say, 20 years. And of course, we want to increase the repetition rate of the attosecond sources in order to increase the signal to noise of our measurement. We would like to have high brightness of the attosecond pulses. And this is related also to the last point in this with the extreme temporal resolution, in the sense that we would like to be able to do an XUV pump probe experiment in which we have attosecond probe, attosecond pump. But for achieving this, we need to increase the brightness of our source, and the free electron laser, of course, is going in this direction. But I mean, we would like also to do this in our tabletop system, and this is at the moment feasible only in very few laboratories. But I mean, it's one of the direction. Another direction which is actively researched is the extension of the spectrum of the XUV pulses toward the X-ray. Basically, this is also something in which I've been very active in order to add the chemical sensitivity to the experiment, in the sense that if you have, for instance, if you are interested in molecular system for biological systems, then you can go to the water window where you have absorption edges of carbon, nitrogen, oxygen, and you can have a look of dynamics happening in a specific atom on your system, which could be quite interesting. And then, of course, if you're interested in chiral sample, then you would like to have polarization control. And these, as we may mention briefly later, is very difficult with the I-order harmonic generation. It's easier with the free electron laser, but anyway, this will be somehow required. So all these fields are actively investigated, and I think we will hear about also about some very interesting experiment that we can do with polarized light from Olga Smirnova. And considering the extreme temporal resolution, also in Francesca Calegari's talk, I think I guess we will hear about the generation of very short UV pump pulses. But I mean, this is actually investigated, and there are credits case for many people, also people participating to this conference. Then, of course, we have sample manipulation. And from this point of view, depending if you're looking at harmonic spectroscopy experiment or pump probe experiment using the harmonic source as basically the pump or probe pulse, we may want to align and orient our gas sample. We need to manipulate complex molecules in order to put them in the vacuum. And of course, we may be interested in what's happening in a liquid, in the sense that we may want to see how a molecule interacts with the solvent, for instance. And I think we will be hearing also some very interesting results from Hans-Jakob Werner in water, which is going in that direction, which is also very actively investigated. And of course, then if you go to solid, you have other problems in the experiment, because they may scatter, you may not be able to get a reasonable large sample that you want to investigate. Then if you look at the detection there, I mean, as I said, the detection that you do is related to the amount of information that you are able to collect from your experiment. And in these respects, you may want to acquire, for example, as we heard, you may want to acquire photoelectrons, but then it could be useful to relate these photoelectrons with their ions they come from. And so you want to have coincidence detections of some kind, like, for example, you want to relate mass spectrometer plus PMI, you want to do covariance or coincidence, you want to have multi-hit detectors, which is experimentally quite challenging to deal with. And you may want also to perform an experiment in which you have a combination of detection techniques. For example, you may want to have photoelectrons or photoions plus photons. And of course, this will enable you somehow to disentangle all the information, or the wealth of information that is in your experiment. So now I will focus a little bit on the high-order harmonic generation, which is the source, the main source for attosecond experiment, the main attosecond source. Basically, this is process, this is a very, I know you're probably familiar, I will just go quickly through. You can interpret this phenomenon in the framework of the three-step model, in which you have the tunnel ionization from the external laser field that detaches an electron from the valence shell by tunnel ionization, and then you have propagation in the continuum driven by the external electric field, and then you may have recombination, and of course the energy gained by the electron, the kinetic energy of the electron, is released through the emission of the XUV photon. So this is how it appears, our spectrum. It's usually, since the process is repeated periodically every half cycle, then you have a spectrum which appears as the whole harmonics of the fundamental frequency, which are separated by twice the frequency of the fundamental field. And then this spectrum extends up to a cutoff, which depends on the ionization potential of your sample, plus 3.17, the ponderomotive energy gained by the electron. And this is proportional to the intensity of the driving field, multiplied by the wavelength squared. So in order to increase the spectral extension, you may increase a bit the intensity, but you may want also to go to longer wavelength, which has been, let's say, a direction that has been very actively investigated in the last year now. Many laboratories have quite huge spectral extension toward the X-ray. Of course, this in the temporal domain corresponds to the emission of a train of attosecond pulses that can then be, for many experiments, you want to isolate only one attosecond pulse to be synchronized with the pump pulse. And for doing so, there exist several techniques. Now, I don't go into detail, but this is also a topic which is very actively investigated, both for the generation and for the characterization of isolated attosecond pulses. And then, last but not least, when we talk about high-order harmonic generation, phase matching is quite an important aspect to take into account for, let's say, attosecond technology. So for optimizing our source, in the sense that you don't generate harmonics from a single atom or molecule, but you do this from an ensemble. And of course, you have the coherent superposition of all the pulses emitted by or the light emitted by the ensemble. And roughly, we can say that the phase matching condition depends on the gas target that you're using, on the driving laser wavelength and intensity, and on the geometry of the interaction. This is very rough. Now, I wanted, when I prepared this kind of review, to show some of the results that have been obtained recently from some groups. But then what I found out it was that it was kind of impossible to acknowledge all of them. And so, like, I would like to point you that we are organizing. I will be chairing an AutoCamp virtual winter school next February, targeted to early stage researcher, specifically on attosecond technologies, in which we will invite people that got very interesting results on all the challenges that I've been mentioning. And this could be quite interesting to check out later this year. And there will be details coming up. So now I'd like to show you something that we obtained in our lab. Basically, the idea is to optimize the high-order harmonic generation process. And for doing so, we used the femtosecond laser micro-machine device, so channels done by femtosecond laser. The idea was to combine basically high-order harmonics with micro-fluidics. So try to do some kind of phase matching optimization to have a bright source of attosecond pulses. This was done in collaboration with Rebecca Martinez-Vázquez and Roberto Zellame of my institution, the Institute for Photonics and Nanotechnology in Milano. And here you can see, well, there is a cartoon of how it works, because basically we use femtosecond laser irradiation followed by chemical etching to get some channels, some 3D structures in which we can inject some gas, and then we can inject our laser beam for doing the interaction to do high-order harmonics. And here you can see two pictures performed. I mean, one is with a camera and one with a microscope for two example of this kind of chip that we did for doing high-order harmonics. And the good thing about this method of this microfluidics method for generating this channel is that it has high accuracy, 3D capabilities, but also very fast prototyping, so you can do a lot of tries and find the best configuration. Now, this is a little, I mean, just a comparison. Usually what we do is to use a gas jet. So like this is the standard configuration that we use for generating harmonics. We have the pulse gas jet. Basically, we can have a high backing pressure. The gas dimension, the interaction dimension is 100 of micrometers. And then we are, of course, the problem is that we are a repetition rate which is up to 1 kilohertz at most, but we cannot go higher. And then if we use instead a microchannel, we can have a continuous flow, and we can have a pressure, like usually the pressure that we use is less than 1 bar, and we can have an high intensity inside. This is not new. Of course, you can say like this has been proposed, the use of this kind of hollow channels for generating harmonics many years ago from Kaplan and Mornay group, very successfully. Which is the difference? Well, the difference is that here we can basically manipulate the shape of these channels in a very effective way. And for instance, here I show you a capillary. Here you have a long capillary in which we can send the beam, and then we can inject the gas from different places within the capillary, for instance, and we can try to manipulate the gas density. So here, this is the experimental setup that we use. So it's a standard generation chamber, and this is the spectrometer that we use to acquire the harmonics. This is really a standard setup. And here you can see a picture of the chip, which is inside the PMMA case, and it could be, of course, aligned manually and with motorized translation stages. And this is in air, and you can see the mode transmitted by this small chip. And here was some of the first measurement that we got. This is like a comparison between harmonics in a chip, one of the first prototype, and harmonics in pulse gas jet. This is a sketch on the right hand side at the upper right corner. You can see a sketch of the chip, and here you can see basically the spectrum. The blue one is the spectrum within the chip, and the red one is the spectrum from a pulse valve multiplied by 10. And of course, this is in the optimized condition, so you cannot really compare because the gas density, of course, is different. But what you can see is that in our setup optimized condition and with the same driving pulses, we can get an extension of the cutoff, which is quite consistent. constant, and we can also obtain quite a huge increase of 1 order of magnitude at least of the signal, which was really a nice result at first. And in this, we also checked how the harmonic spectrum depended on the gas pressure that we put in the chip, and also the cutoff frequency. And here you can see a sequence with pressure changing from 25 millibar up to 1 bar like the harmonic spectrum generated in the chip as a function basically of the pressure. And you can see how it changes quite a lot, the shape and the extension, the spectral extension. And then in order to understand what was going on, what we did actually, Anna Ciriolo, that is my postdoc working on this topic. What she did was to do perform some calculation with COMSOL in order to see how the gas propagates inside the channel. And what we find out is that if this is basically the gas density profile inside the channel, and it's almost flat. So what happened in this chip is that it is nice, we can put the gas inside from several channels, but then what we get is just basically a flat density profile. In order to further understand, because we are collaborating with Valer Tosa, who is doing calculation with the propagation inside the channel of both the XOV generated and the driving pulse. And here, and here you can see for different pressure how we are kind of able with this calculation to basically reproduce the shape of the harmonics that we get in the channel. So with COMSOL, we are able to understand which is the gas density profile inside the channel, and with Valer calculation, we are able somehow to predict kind of what we expect. And so the next step will be to make a second generation chip in which we modify something in the interaction in order to optimize the process, to optimize the phase matching. This can be done with different knobs. We may change, for example, the diameter, make a corrugation in the channel, as already Captain and Mornane did some years ago, demonstrating that this could be useful. But we can also try to modify let's say the density along the channel with a different scheme of nozzle shape and dimension. And what we find out is that in order to have a modulation of the gas density inside the channel, we need to basically have nozzles. And this is a scheme of a second generation chip in which we have nozzles, which have this shape. Basically, this is the microscope image of one of those De Laval micro nozzles that we use. And then we have this outcome window for the gas in order to be able to have kind of a molecular beam inside the channel. And yeah, with this, if you calculate the gas density profile in this new second generation chip, that's the blue one as compared to the red one, which is the first generation. And you can see that here you achieve indeed a modulation in the gas pressure. And this is the experimental results in which you see that with those nozzle, indeed, you have an increase again of the signal, of the harmonic signal quite a lot in the plateau region. And then also in the cutoff, the shape is different, but basically it's like you don't have really a decrease in the cutoff. And then we also find out that if we want to improve the gas density modulation, of course, we have to achieve a better, let's say, quality of the gas transport outside the chip. And for doing so, we try to use a single exit instead of those multiple exits. This is the scheme. So you have the inlet of the gas coming here, and then you have this big outlet. And the challenge with this is that you still need to have a channel in which the beam, the fundamental beam propagates. So you cannot just make a big, huge hole. But with this new configuration, basically what you get is that it's like you get better, an increase in the modulation of the pressure. And here you can see that this is two harmonic spectra acquiring the same condition for these two devices. The blue one is the one with the single exit, and the red one with the multiple exit. And here you can see that you have basically a change in the shape of the spectrum and an increase again of the harmonic emission. So in general, this approach can succeed in getting you a better signal. Now with Valère's suggestion that he did, I mean, like he suggested as we're thinking about how we can move those nozzles in order to obtain something like a quasi-phase matching, or at least change the phase matching condition. And he suggested that the distances we can put our nozzles in a non-periodic structure. For the moment, we are still doing this, so it was just this was just a first try. But what we see is that if we change the periodicity of those nozzles, as we do here, basically we can change quite a lot the shape of the spectrum, which means that if now we perform calculation with full propagation and in different conditions, we may be able to optimize the quasi-phase matching condition and to get really bright attosecond pulse train, and in the future attosecond pulse from this. Now I will do like a summary of these results in some perspective. Basically, what we tried was 3 generations of chip for high order harmonic generation. These 3 geometries lead to different gas density profiles, and of course the yellow one, the last one, is the best. And if we compare the harmonic spectrum generated in those three chips, what we can see is that we were able really a lot to optimize the signal and change the spectrum. And I remember you that as compared to our optimized gas jet, this is pulse gas jet, this is 10 times more. The beginning, the blue one was 10 times more. So here we are scaling it quite a lot. We want to quantify it. So next step will be a measurement of the number of photons, which is needed, of course, to give a number on the intensity of this bright harmonic source. As a perspective, one thing that we would like to introduce is the possibility with this chip to do spectral filtering, in the sense that we want to filter the XUV with respect to the beam, the infrared beam, the generating infrared beam. And this can be done introducing basically a slight curvature. This is really unlayered, but a slight curvature in the channel, so that the infrared follow the channels and the XUV go straight. We tried this with the first prototype some time ago, and we obtained an attenuation of the XUV of a factor of 4, and then an attenuation of the infrared, which was a factor of 100. With respect to metallic filter, they usually have an attenuation which is, of course, many order of magnitude more, but they also have windows of transmission, and depending on the experiment, like this could be really a problem. So somehow, like this could be optimized, our filter could be optimized to be useful in some experiment. And then another thing that we would like to do is to try to do elliptically polarized high order harmonics in a chip by adapting again the approach proposed by Margaret Murnane a few years ago, quite recently, in which we have beams with the circularly polarization that are interacting in one point. This is like the design of the chip is not trivial, but I mean, we believe that we may try to do something, and we have a spectrometer that can do the full characterization of the polarization of the light. That is should be in place at the end of the year. And then the other thing is all the results that I've shown you have been done driving with the standard ISFR laser, and we have had a cutoff which is up to 200 EV, which is already quite nice. But as I mentioned, one of the direction which is very important now is to go toward the water window. And for doing so, we would like to couple our OPA at 1.5 micron with the chip in order to get bright emission also from the driven by the OPA, so that we can increase the cutoff frequency. Here show results that François Legaré and Bruno Schmidt obtained at ALS some years ago. It was actually a few years ago. We participated in this experiment. Basically, this is like harmonics driven in a cell with OPA at 1.8 with a mid-IR sources 1.8 micron, and we believe that so we will be able to arrive up to the oxygen K edge with our spectrum if we couple the harmonics, the chip with our OPA. So to conclude, We have, obtained in our lab high-order harmonics in a microstructured device, in a chip that could be a bright source. We believe it's a bright source of XUV radiation. And so microfluidics can be used as a technique for control and shaping high-order harmonics. And if we now use this chip coupled with a mid-IR source, we may be able to generate isolated attosecond pulses in a water window, and these may be bright. We don't know yet how much, and this will be the subject of the investigation of the next year. This is the group of people that is working with me in Milano. And in particular for this work, I would like to acknowledge Anna Gabriella Ciriolo, because basically this is the activity that she performed in all her PhD and postdoc activity on the chip. And then finally, I'd like to take a minute to advertise that we are hiring early stage researcher. We are offering PhD position in a Marie Curie innovative training network called SmartX, which aims at the study of ultrafast X-ray spectroscopy in materials, in solids. And I mean, if there are people interested that you may know, please share the news. Some of the activity within this network will be strongly correlated with the ATOChem cost action as well, because there are a lot of common interest in. And with this, I thank you all for your attention with 1 minute early. Thanks.
So thanks a lot, Katarina. Thanks a lot for very interesting and fantastic, promising results. And thanks a lot for keeping in time also. And we have already questions. So we have, for example, see that I came in the right order here. Yeah, somebody else says it's excellent talk, but Hans Jakob Werner asks the following question. He also says it's a great talk. And then how large is the predicted increase in photon flux in the XUV compared to free focusing? Do you also have a prediction for the water window?
Okay, that's a good question. Thank you, Hans. I would wait to do a prediction for the water window before we need to do the measurement of the absolute photon flux with the 800 and in the current configuration, because as I said, at the moment we don't have a quantitative comparison, just a qualitative one. So we have the feeling that, let's say, with the 800 source, at least we have one order of magnitude, which was like a kind of very easy to achieve. And then with the manipulation, we can achieve another factor maybe of, let's say, 5, something like that. But I mean, before being able to, I mean, and this is, this is not compared to the infinite cell. This is compared to the pulse gas jet at 10 Hertz. So it's like we know that this is our standard configuration, so we know that the density there is high, but we didn't ever compare with the free focusing. So we may want to do that, but I think the best way will be to give a number of photons, which will something that we need to, unfortunately, we get slowed a little bit with the lockdown, but I think this will be something that we are doing in the next few weeks, because we have a calibrated detector and we can just acquire the spectrum and make the measurement.
You can just put your questions if you have more questions. I will see them. Okay, then I've one more. Marius Lehmann asks, are you going to look into temporal structure of high harmonic generation radiation generated in the chip?
Yes, yeah, this is a very interesting question. I mean, like, we need to study how these harmonics develops inside the chip, because of course, like, you have this long interaction. And I mean, we expect it to be a train of attosecond pulses, but yes, we are indeed going to see this. And what we want to, and also we would like to generate isolated attosecond pulses inside the chip. So this will also be another step. So what we're going to do now is that we may already use these sources as a source of train of attosecond pulses for doing some kind of experiment with femtosecond time resolution, but then basically we have another beamline in which we will go on by characterizing the temporal structure of the harmonics and also generate isolated attosecond pulses. We need to do so with the mid-IR sources though, because our 800 nanometer source is not CEP stabilized. So we need to do this with the OPA, which has the CEP stability. Otherwise, this is not experimentally feasible.
Okay. We have another question from Pascal Solier. And he asked, did you look at the angular distribution of the middle harmonics? You probably could phase match selectively short or long trajectories by modeling the gas density.
Yes, so we looked into the angular distribution of the emitted harmonics. Actually, this happened, let's say, by chance at some point, because we were acquiring this the spatial shape of the harmonic spectrum, and we saw that indeed there is, I mean, as soon as you change the sample or you change the pressure, you can see that this is changing, and this also will need additional characterization, because at the moment we have no prediction, exact prediction of what's going on, but indeed we are going to investigate this further.
So we have one more question. They're popping up here. See if I can just see it. So Barry Brunner asks, will you try generating high harmonic generation in the chip with wavelengths longer than 15 micrometers? Is there a limitation to the wavelength you can use in the chips?
Okay, I'll make it short. Basically, are we going to use longer wavelength? We may. We have an OPA at 3 micron. And we can tune the central wavelength of our OPA up to, let's say, 2 micron, which is the limitation. Well, basically, you want to have coupling. And this means that probably, I mean, like, for example, with 3 micron, you may have losses, a lot of losses. So you may not be able actually to really generate efficiently. But I mean, first we need to see how much is the increase in the harmonic emission from the OPA at 1.5, and then we will be probably able to do, let's say, because I mean, if we put a lot of pressure there, we may be able to counter interact the unfavorable phase matching condition, and then like we can move to longer wavelength as well.
So, no more questions from the audience. Can I ask a more simple-minded question? Since it looked like you had at least 2 orders of magnitude higher intensities than you started with, I'm not sure, perhaps it was even more. Does this mean that you are very close to being able to do pump probe with the XUVs?
I'm not sure I can say so. First, I would like to have a measurement of the photon flux and of course the manipulation of the XUV after the generation. This is also something which introduces a lot of losses. So before saying that we can do XUV pump, XUV probe measurement, I mean, there's still some road to go to, but I mean, like, of course we are moving toward that direction. So
okay, I think that's I don't see any more questions, and we are more or less close to the next talk. So I would like to thank you very much for a very interesting and
thank you,
and enthusiastic talk. And remind everybody that you can meet Katarina afterwards in the Meet the Speaker sessions. And we go on to the next talk, which will be given by Frank Lépine. The title of the talk is Correlation Effects in 2D Molecules under XUV Radiations, the Present and the Perspectives. So welcome, Frank. And go ahead.
Yeah, thank you, Eva. So we'll try to share my screen. So Does it work?
Yes, it works.
Yeah, okay. Thank you. So yeah, it's a pleasure to be here, even if we cannot meet in person, of course. And I would like to talk about experiments that we perform where we try to study processes that are induced by XUV radiation. So Fernando mentioned that in all these attosecond experiments, we have XUV pulses, and we have to ionize somehow the molecules and see what happens after the ionization. And here I would like to give you some general ideas about what's going on and what we are doing now, and maybe what we can do in the future in connection to the AutoChem cost action. But first, I would like to thank people in my group in Lyon that are strongly involved in all these results I will show you, and especially Marius, Hervé, and Alexis Boyer, who have performed most of the experiments I will show you. So, yes, as Katarina mentioned, what we have in an attosecond experiment, it's a light source that provides XUV photon and ultra short pulses, and Katarina showed that we can really manipulate these pulses, increase the photon flux, change the wavelengths, and so on, and manipulate the duration. But what happens in these experiments in any case is that we have photons with high energy and we have light with large bandwidths. And of course, on the molecular point of view, the large bandwidths means that we will be able to superimpose states and create ultra-fast coherent processes on very short time scale. And of course, the high photon energy tells us that most of the time, the interaction will lead to ionization and may involve many degrees of freedom, electrons and nuclei. So, as already mentioned by Fernando, what we have done in the past with attosecond pulses, what the community has done in the past, is try to study relatively simple systems, atoms, small molecules, and we start to see experiments on few femtosecond time scale on more and more complex systems, small amino acids and other or chiral molecules, for instance. And we have experimental results, but also theoretical results that predict these dynamics on very short time scale. I would, let's say, distinguish experiments where what we try to do is to create a process that is essentially a one active electron process. So we try to create a wave packet that can be, ideally, a wave packet of one electron propagating very quickly through the molecular structure. And there are a few examples of that in the literature. But there are also processes that I would call correlation-driven. Of course, correlation is always important when you try to describe a molecule. It changes the electronic structures, it changes the properties, and so on. But here I'm talking about processes where many electrons are active. And I'm talking about processes where if there is no correlation, there is no process at all. And we all have heard about the correlation-driven Hall migration. That is a situation where you have the role of shake-up states or the role of multi-electronic states that create specific dynamics. And we also know a lot of examples of ICD, experimentally and theoretically. And the point is that what we have done so far, it has been done on relatively simple systems, and moreover, it's already very complicated on the experimental point of view and on the theoretical point of view. And of course, if we want to move forward to attosecond chemistry, we have to connect what's going on very short time scale when the molecule interacts with a short XUV pulse, and what's going on very long time scale when the molecule has reacted to the excitation. So if we want to be able to connect if we want to be able to connect the attosecond excitation to the reactivity, we need to be able to connect attosecond, femtosecond, picosecond timescale, and to connect electronic and nuclear degrees of freedom. And eventually what we want to be able to do, and Fernando and Katarina mentioned it before, we want to be able to observe this kind of processes on different timescales, and eventually we want to be able to control the process. So what I would like to tell you here, it's really about what's going on when a molecule is excited by an XUV pulse. And as Fernando mentioned, the main thing that happens is it's an ionization process. And I like to use this very well-known representation of what happens to a molecule when it is ionized by high-energy photon. So that's a representation that basically that is just the cationic states that are produced after ionization and the binding energy of these states. So we start from a neutral system. It's excited by an XUV pulse, and we try to ionize this molecule, and we try to remove one electron. And then we create a cation. And here it just represents the cationic states that are produced after ionization. And okay, we all know this representation. The height of the peak tells us how much this particular state can be represented as a one-hole configuration. So that's a configuration where we try to remove one electron from a particular molecular orbital. And the cation that is created is just a cation with one hole in this particular molecular orbital. But when the photon energy increases, we have access to more cationic states, and what happens is that we can have situations where the states that are created in the cation are not anymore one-hole configurations, but they have to be a combination of configurations, including two-hole, one-particle configurations. So configurations where many electrons are active. So that's a situation that you can see here. So the same situation, we try to remove one electron from a particular molecular orbital, and it creates not a single, but two possible states, two different binding energies that are represented by these kind of configurations. And when the photon energy gets higher and higher, what you have, it's a situation where correlation plays a more and more important role. And you can end up with a situation where all these states that you have created, or this shake-up state that you have created, becomes very, very important. There are so many that it's actually form a dense structure that Lorentz Sederbohm called correlation band. So that's basically what I would like to discuss now. If we have a molecule, neutral molecule that interacts with a high energy photon, all these states can be created, and then we will try to probe this state with a weak infrared field. So, yes. So to do that, we use a relatively standard setup that is using high order harmonic generation. So we start from femtosecond laser. We can create harmonics with a gas cell, and this harmonics is indeed a femtosecond or an attosecond pulse or attosecond pulse train, and we can recombine with the infrared pulse. We can recombine the two beams and focus them on the molecular beam, and we can use, for instance, a spectrometer. Here it's a velocity map imaging spectrometer, so it's a spectrometer that measures ion or electron velocity distribution. And we can try to measure how this signal, for instance, the velocity distribution of the electrons, varies when we change the delay between the pulses. So that's what we have done on this example. Here we use a simple system. It's naphthalene, it's a neutral molecule. And indeed, that's the spectrum of cationic states that can be produced after ionization of the neutral molecule. And that's a calculation performed by Victor Després and Alexander Koulev from Heidelberg. So what we do in the experiment, we produce these cationic states and we try to probe them using the an infrared pulse. So schematically, you can basically represent the situation like this. XUV ionize the molecule, it creates cationic states, and we probe these states with an infrared probe by ionization, and we try to measure this electron. And that's how it looks like. So here you can see the electron kinetic energy as a function of the delay between the two pulses. And the color scale is just the number of electrons. And you can see that you have a quite complex structure in the kinetic energy spectrum. And you can see that you have very fast dynamics occurring at different kinetic energies. So you can select slices of this spectrum, and you can see that you can extract a time scale for the decay that you observe at different electron kinetic energies. And you can see that the time scale that you can extract is typically few 10 femtoseconds, and it depends on the kinetic energy of the electron. It increases with the kinetic energy of the electron. So from now, we can try to understand what's going on and what are the main ingredients that we need to understand this measurement. And to do that, we have a collaboration, long-term collaboration with Victor Desprez and Alexander Koulev from Heidelberg. And many years ago, we collaborate to develop a model that includes ADC calculations and MCTDH calculations. And that's a model that combines a very good description of the electron correlation, but also non-adiabatic couplings, so the couplings between electron and nuclear degrees of freedom. So that's what Victor and Alexander did. They computed the ADC spectrum, so the cationic states with ADC. Then they could build the potential energy surfaces corresponding to all these states. And then these potential energy surfaces are coupled, and they can use MCTDH to propagate the population through all these states. And what they see is that if they consider only the dynamics of the main states that you can see here, then you see a very, very fast dynamics that is very different from what we have experimentally. And moreover, they see a different behavior. They see that the time scale is actually decreasing when the photoelectron energy increasing. So that's what you see here. But when they really take into account all the states, all these shake-up states, and they increase the number of states that are involved in the model, then they are able to actually reproduce what we have observed experimentally. So they are able to reproduce the fact that the time scale increases with the photoelectron energy. And here you can see that the time scale that they have calculated is very close to what we have experimentally. And from this, there is still a difference, but we know that from this, that if we include more states in the calculation, it will converge to what we have experimentally. So it means that from this calculation, we learned that the time scale that we measure is actually the non-adiabatic relaxation. So that's energy that is put initially in the excitation in the electron that is transferred to the nuclear degrees of freedom. And what we learn also is that it is a situation where non-adiabatic relaxation occurs, but where correlation is very, very important. And we have to include correlation with very accurate representation of the shake-up states. So, of course, we might wonder if this kind of process is actually something that is specific to this molecule or to small systems. And we have performed other experiments on adamantane that is like a very similar structure, but just a cubic one compared to naphthalene. And here again, we observe using time-resolved photoelectron spectroscopy, we observe again the same behavior, short time scale of relaxation, and increase of the time scale as a function of the kinetic energy of the electron. But still, we have some examples that it seems to be a general process, but now we would like to know how much we can extend this process to a much larger system. And to do that, we will actually try to study molecules like HBC or fullerenes. Here the experiment is the same. We start from a neutral molecule, and the neutral molecule is ionized by an XUV pulse, creating cationic states. But in this situation, we have many more states. The situation becomes even more complex than what we had before. And that's where we start to see clearly what I called before correlation bands. So dense structure in the electronic spectrum where there's a very large number of multi-electronic states. And we create this band structure with XUV, and then we probe it by using a second pulse, a weak pulse in the infrared, and we study the ionization again. And that's the signal that we have. So this signal of ionization as a function of the delay. And what you can see here is that you can extract from the measurement a single time scale that is typically 50 femtoseconds. So you can obtain this time scale and you can try to see if it changes when you change the higher intensity or if you change the XUV photon energy. And it does not. You can see it here. You can change up to a certain extent, of course. You can change the higher intensity and it doesn't really change the time scale that is measured here. And you can change the photon energy, you can increase it. And what happens in that case, you can increase the photon energy, but you will always, here at this energy, you will always create the same band that is going to be probed by the infrared. So basically, we have a situation where we measure one time scale for this specific molecule. And we try to do that for a number of other molecules. We have done that for anthracene, pyrene, and so on. So these are the PAH molecules, and we have tried to do that also for diamantoids, diamantan and diamantan, that are cubic molecules, and for fullerenes. In each case, what you see is that you can get a single time scale for each molecule, and it doesn't really change within the error bar when you change the higher intensity or when you change the photon energy. So, of course, we can just plot what we have measured for the different molecules. So this is the time scale extracted for each molecule as a function of the number of valence electrons in the molecule. And what you can clearly see is that it seems to be a very smooth augmentation of the time scale for the pH, and they seem to match a very simple evolution, while you don't have the same behavior for the diamantoids or for the fullerene, or at least they belong to a different curve. So before I showed you that we did some calculation using ADC and MCTDH for naphthalene. Of course, we cannot do that for fullerene or for HBC. So we had, in order to try to understand what's going on, we had to use a different methodology. And what we did, actually, we developed a model, again with people from Heidelberg. And this model is simply based on the equivalence between non-adiabatic relaxation molecules, so electron vibrational coupling in molecules, and electron phonon scattering in solid. And you can use the Fermi-Golden rule to compute what is the lifetime of the excitation in the correlation band that we want to study. But to do that, we actually need to describe the density of states. You need to model it if you want to have a simple analytical formula. And what we did is to assume that the density of state is actually linear as a function of the binding energy. And if you do that, you can actually develop a very simple calculation, and you end up with this very simple formula where the time scale of the excitation in the correlation band depends on only on two parameters. NCB, that is actually a parameter that depends on the strength of the correlation, of the electron correlation, and tau 0, that is the mean electron scattering lifetime. So this hypothesis of the linearity of the density of states, this we could test it by comparing, just by making ADC calculations. And that was done again by Heidelberg, where they computed the ADC spectrum, so the cations state that are formed upon photoionization. And when from this spectrum, we can compute the density of states, and you can see that below the ionization threshold, where we probe the states, you can see that the hypothesis of the linearity is actually very good. And it gets better and better when the system gets larger and larger, of course. So, going back to the results, now what we can do, we can use this simple formula, and we can extract the two parameters based on the ADC calculation that we performed for naphthalene. So what we do, we can use the lifetime that has been computed for naphthalene, and we can use it to determine these two parameters, and this leads to the orange curve that you see here. And this orange curve clearly shows you that this simple formula matches very well the experimental results we have for all the pHs, meaning that a single T0, if I go back to the formula, a single T0 and NCB is enough to represent the behavior of all the pHs. Of course, you can also use the formula to determine accurately these two parameters by fitting the experimental data. And this provides you these two parameters that seem to be universal for this family of molecules. So basically, with a curve, you can predict the timescale that you will obtain for any pH when you try to do a pump probe experiment, and when you try to study XUV-induced processes. Now, looking at the other molecules that you can see here, they clearly do not correspond to the same curve. But what you can do is to take the curve that is obtained for the pH and just rescale the T0 parameter. So here we just assume that N0 is the same, so the strength of the electron correlation is more or less the same for these structures, but we change the T0 based on the known vibrational modes of the molecule of these diamondoids. Doing so, you basically obtain the two curves that you see here. What we have done here, we just took the pH curve and just rescale one parameter according to the vibrational mode of this structure. And you see that it matches very well. So it seems that we can represent the non-adiabatic correlated dynamics in these systems that are induced by XUV by using a very simple model. And what is different from one molecule to another, it's only how we describe the correlation band. It's the nature of the correlation band changes the time scale that we measure. And here you can see that for fullerene, we definitely need something a bit different, which is also probably expected because fullerene is a very specific case. We know that electron correlation has a strong influence in the ionization process. It creates a very strong plasmon resonances at 20 and 40 eV. So probably we need a different approximation to represent the correlation band. So here what I showed you is that, okay, just remind you that correlation bands are completely general features of XUV ionized molecule, and they are due to electron correlation, and we find them in any molecule that is complex enough. And the question here is, what is the role of these correlation bands in XUV-induced ultrafast processes in general? For sure, in some molecules, probably the small ones, this probably does not play a major role because the molecule is not stable enough in that case, but at least for the molecules I showed, and we have indication that it also works for other types of molecule, it seems that it represents quite well the process. What is interesting here also is that everything happens as if the population initially trapped in the correlation band is trapped longer than what you might expect in the case of individual states. So somehow the excitation is trapped for several tens of femtoseconds before it's actually completely dissipated in the molecule. So the question is, of course, in relation to this attosecond chemistry, is the coherence loss in this situation? Probably, but we also have indications that vibronic coherence is maintained in these processes. So that's a question we should try to push. And of course, there is a connection between ionization of XUV molecules of XUV and the interaction with the molecules in connection with the molecular reactivity in interstellar media. So now I would like just to take a few minutes to talk to you new challenges that we have when we try to perform experiments with short XUV pulses, and if we want to connect to chemistry or biochemistry. What I've showed here is actually essentially interaction with between light and neutral, relatively small molecules, or larger molecules, but still neutral and relatively model systems. Ideally, if we want to have a connection with chemistry and other research field, and probably if you have discussion with biochemists and so on, they will ask you the question, can you do that on systems like that? Can you do that, the same kind of experiments on a protein? So here I'm showing just a cytochrome C, that is 100 amino acids, and how is it, or is it possible to study such a system? Of course, we have to study small systems and larger systems, but it's also important to realize that in biochemistry and biology, molecules are usually charged in their natural environment. They are protonated or deprotonated to be more stable. So we also need to be able to study molecular ions, but molecules that are ions before they are excited by pulses. And we need to learn how, and that was also mentioned by Katerina before, we need to learn how to manipulate these complex systems, and we need to learn how to study the dynamics in these systems. And we have to remember also that using ionization, it means creating new charges. It's also what has been used for many years already to increase the reactivity in biomolecules. So creating new charges is always a good trick to manipulate how the molecule evolves, how it fragments and so on. So what we can do now with the tools we have is actually to do it on very short time scale and to observe in real time what's going on. And to do that, we have developed a new experiment that's called Kashmir. And that's an experiment that combines ultra-short XUV pulses and electrospray ionization sources that is able to extract from a liquid sample. It's able to extract a molecule, to isolate the molecule in the gas phase, and to produce the molecule, even very complex, in a charged state. And then we can interact with the light, and we can measure the result of the interaction and study the dynamics. Of course, going from neutral to ions makes the experiment way more complicated, because we use many orders of magnitude of signal, and the manipulation of the ions is very complex. But I would like to show you an example of what we can do. And here I choose a protonated razor prime. So this molecule, it's a model system in biochemistry. It's used for test in many analytical chemistry protocols. And this molecule it's an alkaloid. And it's a drug that is used for treatment of hypertension. And it's a molecule that is very well known. And basically what we know very well how it fragments when it collides with atoms and so on. And what we have done here is to excite the molecule with a short XUV pulse. Here you can see the mass spectrum that you see when the protonated reserpine is just fragmented by collision. And you can see specific fragmentation patterns that are known and identified. And here you can see the results of the excitation by the XUV. You can see actually new fragmentation peaks appearing, for instance, these peaks that are specific to the XUV excitation. So here we are dealing with a molecule that is protonated, so it's a cation, it's charged. There's a proton sitting here. So what's going on here? Well, we start with a molecule that is protonated, and we ionize it with XUV, and we try to probe what's going on with a weak infrared pulse. And you can see the result of the experiments here. You can see.
I have to remind you about the time, Frank.
Yes, I'm done. I'm just, yeah, that's my last slide. And just to show you that you can actually see very, very short time scale. And that's a process where removing one electron create a hole, and the hole will move to one side of the molecule within few 10 femtoseconds. And the dynamics is essentially driven by the dynamics between the interaction between the proton and the hole. And that offers new perspective, because here we have used these dynamics to create new fragmentation schemes. So that's a summary of what I wanted to show you. We can actually study ultra-fast dynamics induced by XUV in molecular ions. We showed that we can have proton-hole driven reactivity on few 10 femtoseconds, and you have this new apparatus to perform experiments. And of course, if you are interested to do experiments in our lab, or we can also bring the machine to your lab, the cost action is definitely the good place for this kind of collaboration. But I think this offers new perspectives in terms of chemistry. And with that, I would like to thank the people that have been working on this project, and you for your attention.
So thanks a lot for a very rich talk. We have already several questions. So we start with Amel Said's first question, which is like this: when you increase the IR intensity, are you considering the Stark shift of the cation? Sorry, of the cation states, or is it irrelevant because of the IR intensity that is not high enough, so that is on the dressing?
Yeah, it seems we don't need to consider it. Basically, what we did experimentally is to test that what we measure is actually independent on the IR intensity. So we have seen no effect of varying the IR intensity, and we have done experiments at very low higher intensity, really at the limit of what we can do experimentally, 10 to the 10 watt per centimeter square. And between this low intensity and high intensity, we don't see any effects. But it's not included in the calculation, and that's not an effect that is taken into account in what we see. Most probably because what we do when we probe, we essentially probe with a very small number of photons. And when we increase the IR intensity, what we do, we create more fragmentation and so on, but that's not what is observed in the experiment. What we observe in the experiment, it's only the ionization by 1 or maybe 2 IR photons. And the other processes are just not measured.
Thank you. We have a question from Jochen Küpper. He has a question on the possible lost coherence. As you work on practically isolated molecules, would one not expect the system to behave fully coherently for timescales limited by the interactions with the rest gas and black body radiation, which is on a very long time scale, maybe nanoseconds. That isn't the appropriate question. What subsystem of the full Hamiltonian do I have to look at to see the coherence? Did you get that complicated question?
Yeah, sure.
Yeah.
Yeah. No, I think it depends what you call, of course, coherence. What I'm talking about here, it's really when we create initially the electron wave packets. In the simple case, you can imagine that you have created a wave packet, and the wave packet, it's a pure electronic wave packet, and it can be coupled to nuclear degrees of freedom. Of course, if the coupling is, let's say, simple enough, then you can maintain the coherence. So it's known for many, many years. You can have a vibronic coherence, but you can have also electronic coherence as soon as the phase somehow is not lost. So what happens is that you can actually, if there are many degrees of freedom that are coupled all together, then you can just lose the coherence of the initial wave packet that you have created. So you can have an electronic wave packet, but if this wave packet, if the electronic states are coupled to nuclear degrees of freedom, and then these nuclear degrees of freedom are all coupled together, eventually you can have a loss of the coherent properties of this wave packet. That's not a big surprise. I think that's quite known. But eventually, of course, if you would be able to measure the phase, where the phase went to, and so on, then somehow you can say that the system remains fully coherent. But just the question is, if you can create a coherent electronic wave packet, how much it will survive, how much its motion will survive before it gets lost by the coupling with other degrees of freedom.
Okay, Amel Said has one more, or at least one more question. So this second question is, before the multi-configuration time-dependent Hartree calculation, are you considering the electron PES along one nuclear degree, or are you also looking at other coordinates?
Yeah, basically we are looking at all the active vibrational modes. So it's not 1D potential energy surface. It's actually all the cationic states, or most of the cationic states, and all the nuclear degrees of freedom, all the coordinates that are active in the dynamics. So it's not a 1D. Of course, I showed only one coordinate, but this is done for all the active vibrational degrees of freedom.
Okay, and we got a new question from Valérie Blanchet. Could you come back on the tau zero, on the physical meaning of the tau zero?
Yeah, I mean, so basically we have this formula that can predict the time scale of the pH, and there are essentially two parameters, and one is tau zero. You can understand as basically the mean lifetime of an excited electron, how much time the excited electron will live before it scatters. On the molecular point of view, that's just the relaxation. If you think in terms of many potential energy surface that are coupled all together, that's the typical time scale of relaxation between two of these potential energy surfaces. So that's the molecular point of view, or the solid state point of view.
So we have a final question from Amel Said, which I think we can manage, which is, can you extract a degree of coherence?
Sorry, I didn't hear. Can
you extract a degree of coherence?
A degree of coherence? No. I mean, not for the moment. I mean, these are, these are already very complicated experiments, and things that we can do with photons, for instance, are much harder to do with a complex molecule. But that's definitely yeah, something to think about and to look for. But first, we have to define what are the conditions that would make the coherence survive long enough. Is it, can we create this wave packet and it can survive for a very long time, or his initial coherence will be completely destroyed? First, we have to show that we can have the coherence in the experiment, and then we can characterize it. So we are not that far for the moment.
Okay, then we are actually exactly in time for finishing the session, and I would like to thank Frank and also Fernando and Katarina very much for their very interesting presentations, and remind everybody of you that you can now join them to have a more informal discussion in this join the speaker, or what meet the speaker is it called. It's there on the web page. So this will go on for half an hour, and the next session starts at 11:30. So see you then. Bye and thanks.